So we're slugging through chapter 1, and last time I talked about ideal gases. The ideal gas equation is PV equal to NR bar T. You have that committed to memory. It's a pretty easy equation. You've used it in a number of classes. What exactly is P? Absolute pressure. What is V? Volume. What is N? Number of, we're going to talk about kilomoles because we're using the MKS, not the CGS for the SI. Very rarely will I use pound mole, but a pound mole is something different than a kilomole. R bar, universal gas constant, 8.314 kilojoules per kilomole Kelvin. And this temperature is absolute. So two things have to be an absolute scale. Pressure is absolute. Temperature is absolute. How many people in Thermo 1 will put degree C in there for temperature? Too many. Don't do it. Don't do it. Don't do it. If you have 1 mole, notice there's no kilo on that. If you have 1 mole of an ideal gas, what could be an ideal gas? Something like oxygen, something like argon, something like helium. There's a lot of fluids that behave as an ideal gas. At a temperature of 0 degrees C and 1 atmosphere pressure, it occupies 22.4 liters. Last time I emphasized a liter. A water bottle has a mass of about 1 kilogram for the water in the water bottle, 1 liter water bottle. And so if you can imagine, okay, I have 24 of those, 22.4 of those liter water bottles, that's a size of 22.4 liters. So the specific volume on an amount basis, a molar specific volume, would be the volume occupied by whatever amount you have. So in this case, it would be 22.4 liters per mole for an ideal gas. Somebody says, how many liters are required to fill the space of 1 cubic meter? How many liters are required to fill a space of 1 cubic meter? 1,000. 1,000 liters fills a space of 1 cubic meter. So you could also express it as 22.4 meter cubed. What you would do is just say, okay, let's multiply the top by 1,000 and the bottom by 1,000. And so then that liter, 1,000 liters, becomes 22.4 meter cubed. And then you have a kilomole. So either you work in meter cubed in kilomoles or liters and moles. Molar mass, big M. We talked about that, I think, last time. So what's the molar mass of diatomic oxygen, O2? 32.00 kilograms per kilomole. Oh, my memory's a little faulty. Or is it 32.00 kilomoles per kilogram? I can't remember. Which one is it? Is it kilogram per kilomole? I think it's kilogram per kilomole. And why? Well, somebody defined molar mass first, and that's what it is. And thankfully, if I open up any engineering and science textbook, it is how much mass per amount. So it's grams per mole or kilograms per kilomole, thankfully. It's not flipped and flopped around. If I look in this book, it has a different definition. No. So the molar mass is how many kilograms per kilomole. Okay, let's see. What's the molar mass of H2O? H2O, that's water, H2O. 16 for the oxygen. How much for each hydrogen? 1 for each hydrogen. Add them together, you get 18. So it's around 18. Now there's some change out there, yeah. But you know, if you can get 18, that's pretty good, right? And then that's how many kilograms per kilomole. What's Avogadro's number? Yeah, so it's 6.022 times 10 to the 23 particles per mole. So if I have a mole then Avogadro's number tells me how many entities are in that mole. And so if I'm interested in how many particles, not in a mole but in a kilomole, then it's 6.022 times 10 to the 26 particles or molecules or electrons, whatever you're counting. Avogadro's number is a generalized concept. It's just you use this huge number because there's a lot of particles in a little bit of space or a little bit of volume when you're talking gases and electrons and molecules. If there are 6.022 times 10 to the 23 molecules in a gas, of a gas in a mole, how many molecules are in a kilomole? We just did that. See how easy life is? But I forgot to turn my clickers on, so let me try that now. This may work. It'd be the first time this semester, so let's try it. Oh, come on. I don't like it when it goes in a circle that long. All right, we'll see if we get another clicker question here in a second. But just have your clickers ready, okay? The Zeroth Law and thermal equilibrium. We mentioned already the first law of thermodynamics. What was that all about? Energy is conserved. So it's a statement that energy is conserved. About the second law of thermodynamics. Well, even though energy is conserved, you can't just willy-nilly convert one form into the other form. Actually, there's a preferential direction for the transfer of energy, kind of like from valuable forms of energy to less valuable forms of energy. From work to heat, easy. But it's limited the other way. Heat to work is limited. You can't convert 1 kilojoule of heat transfer into 1 kilojoule of work transfer. Impossible. That's the limitation, second law of thermodynamics. After they did that, they really scratched their head and said, you know, we really need to do a better definition of time and temperature. Like, try to define time one time. You know, just try it. It's really difficult to define something so basic as time. Similarly with temperature, but when they tried to back up, they said, oh, we should have made that the first law. Well, we can't do that. We already have the number 1 used. We'll put the zeroth law. It's more fundamental. So the zeroth law is out there, and I just expose it to you. It says if object A is in thermal equilibrium with object C, think about C being a thermometer, they have the same temperature. We know that. But if object C and object B are in thermal equilibrium, then we can conclude then that object A is in thermal equilibrium with object B, and they have the same temperature. Did you really need a law for that? Probably not. But it's out there, the zeroth law. So let's talk about temperature scales. So what does temperature measure? From hot to cold. Usually we have a temperature scale. If you have a higher number for that temperature, it's hotter. And a lower number means it's colder. So what are the two temperature scales that we like that are the relative temperature scale? Degree C and degree F. C for Celsius, F for Fahrenheit. We also know that we have a lot of water on this earth. So where water basically turns into ice or melts, it does a phase change at 1 atm pressure. What is that temperature where water freezes in Celsius? 0. How about in Fahrenheit? 32. They are the same hot and cold. They're the same temperature, just a different scale. Then the other one is the boiling point. Boiling point at 1 atm pressure. So what does water boil at in degrees C at 1 atm pressure? 100 degrees C. And for F? 212. What is the number of temperature increments between the ice point and the boiling point for water in the degrees C Celsius? It's 100 temperature increments. How many temperature increments are between those two? 180. So between the same cold to hotness on a degree of temperature scale, the Fahrenheit is a smaller increment of temperature change. There's almost 200 for the 100 increments for the degree C. So it's a more refined scale, if you like to use that term. Those are relative temperature scales, are they not? They're relative. And without a lot of justification, you've been exposed to an absolute temperature scale. Which one have you been most exposed to? Kelvin. And so the Kelvin is also a temperature scale, which is an absolute temperature scale. Now, the Kelvin temperature scale is related to the Celsius by what factor? 273. 273. So if I wanted to, I could write an equation and say, give me the temperature in degree C. This is a little different notation, but every book struggles with the right notation. It says, if you give me a temperature in degree C, I will add to it 273 increments of temperature, and that will be the numeric value of the temperature in the Kelvin scale. Does that equation make sense? So if I give you 100 degrees C, that was the boiling point at 1 atm for water, then we get 373 Kelvin. If I give you 0 now, it's 273 Kelvin. True? And then you can think about going down to 250, 200, 150, 50, and you get down to what we call 0. 0 Kelvin. Let me ask a question. This is an absolute temperature scale. Somebody reports, they say, I've observed or made some laboratory measurements. I've observed -5 Kelvin. What are you going to say? Impossible. It's not possible. On this side of where? A black hole. Of a black hole. Okay, well, we're not interested in black holes. At least I'm not. And this class is not, so your fellow students are very happy. So it's impossible to have a temperature below 0 Kelvin. True or false? True. It's true. Think about, what does temperature really measure? I know that I'm eluding a clear definition of temperature. I'm saying it's hot and cold, but on a molecular level, it's associated with the energy of the particles that are kind of bouncing around in a gas or vibrating in a solid or a liquid. And so it's like they all come to rest. I mean, they all come to rest. And there's no more motion on a molecular level. And now, how could you get lower than 0? It's like kind of get broke. Can you get like a negative kinetic energy? No, it's at a molecular level, it's 0. Nothing's moving. So that's what you can think about when you think about 0 Kelvin. How cold is that on the degree C scale? Is it -273? Somebody says, I made a measurement. No, it's not -5 Kelvin. It's -275 degrees C. Is that possible? It's impossible. Oh, they could get -270. They could get -100, but they can't get below -273 degrees C. Now, there's another absolute temperature scale. It's less used, least of the temperature scales used, and it's Rankine or Rankine, okay? And the relationship between the temperature in Fahrenheit and the temperature Rankine is that you add not 273, but that you add 460, round it off. So the temperature in degrees Rankine is equal to give me the temperature in Fahrenheit, and then I'll add to it 460. Somebody says, I'd like more digits than that, Professor. I'm paying a lot of money for this tuition. All right, 459.67. And I know over here we kind of rounded that off. It's 273.15. So there you have it, the 5 significant digits. I really paid a lot of money. I want more than 5. Go get it out of a book somewhere. All right? 3 digits is good enough for most applications. There's 5 significant digits on both of those. Now, so what is the temperature then 32 degrees F, what is it in Rankine? 460 plus 32 is 492. All right, so then I come down here and I'll have 0 degrees R. Well, can I get any colder than 0 degrees R? Impossible. You can't get a negative on an absolute temperature scale. All right. Well, what is that temperature in degree F? Like this was negative 273 for degree C. What is that low, 0 temperature? Absolutely the lowest temperature you could aspire to in degrees F. I'm sorry? Okay, negative 428 is one answer. Here's a little hint. The number of temperature increments between positive 492 and 0 is 492. Just like there was 180 increments between 32 and that, right? So what will this be? This has to be how many increments? 492. So I subtract off 492 from 32, and what do we get? We're kind of going in circles, aren't we? Is it or is it not negative 460? Or try to do this. Take this here equation that we all agreed to and turn it around where I say, I'm going to give you the temperature in degree R, 0. Use that equation to give me the temperature in degree F. It'll be negative 460. Make sense? All right. Now, what about, I left out this temperature up here for the boiling point of water at 1 atm in degrees R. What is that one? 672. Does that look good? All right. So let me kind of emphasize here that if I have a 1 degree C temperature change, that's equal to 1.8 degree F temperature change. True or false? Right? 1 degree C temperature change is also equal to 1 Kelvin temperature change. True or false? That's true. So we can talk about magnitudes of temperature and converting between them, scales, but also remember a lot of times we'll talk about the temperature change. Oh, I started at 20 and I went to 21 degrees C. That was a 1 degree temperature change. How big of a temperature change was that in degree F? 1.8 degrees. Same change in hot and coldness, but the magnitudes are different. All right. We put down this as a transformation. We put down this equation for how to convert. Well, you can work it out and you find that the temperature in degree C, if you wanted to convert, given a temperature in degree F, you first subtract off 32, and then you divide by 1.8 or multiply by 5/9 or whatever, however you want to recall or do that conversion. Before I leave this scale, somebody says, I want you to compare a temperature of 33 degrees F and 0 degrees C. I'll put it over here, 0 degrees C. Which temperature is warmer? Which temperature is hotter? 0 degrees C or 33 F? 33 F. You're very good. Those are the pictures of the people who are attributed to the temperature scale. Celsius, Swedish astronomer, 1744. Oh boy, how long did he live? Not long enough, in my opinion. Not long enough. And then Fahrenheit, the German physicist. There you go. I'm sorry? All right, let's keep going. A temperature clicker question. We'll start it right now. A temperature of 100 degrees C is colder than 100 degrees F. True or false? What I'm going to do is I'm going to give more time, and then what I can do is I can show this. And now people can play and they want to say, is my clicker registering? Well, punch in E and then punch in D and then see it change. See? So I know we got 50 people out there doing the same thing, so it's a little hard to see maybe. But when it gets down to 56, you can see it counting down. You're going to need to lock in on your final answer, okay? Everybody press A, huh? How about we sort of zone in, okay? Everybody zoning in on the answer? You think we'll end at 100% correct or not? Three seconds, 2 seconds? I don't know who's on A. We have 2 people that are on A. That, when I click it, it's now graded true. So 100 degrees C is not colder, but it's just the opposite. It's hotter than 100 degrees F. So thank you very much for your participation. Temperature of negative 10 degrees C is colder than 0 F. And I only give you 60 seconds, or not 30, 60, 30 seconds. Well, what you could do is you could say, I want to take this temperature and maybe convert it to degrees F. Okay? How do you convert negative 10 degrees C over to the Fahrenheit scale? Yeah, you basically negative 10 times 9/5 or 1.8. You get a 14. What about 14 degrees F? Is it colder than 0 degrees F? Doesn't take much to be tricky, right? Or whatever, make it work. All right. What is the correct spelling of this temperature scale? And do you think we'll be 100%? But that's pretty good. Somebody likes A. Somebody likes A. Yeah, raise your hand. No, don't do that. Temperature negative 25 is colder than negative 25. I'll tell you what, let's even change this up. I'm getting tired of these. Negative 40 versus negative 40. I'm going to add here that C is that they're the same. SAME. So there you go. We're off and running. So temperature of negative 40 C is colder than negative 40 F. A, true. B, false. C, hey, they're the same temperature. Same degree of hot and cold. All right, well, we locked in. Guess what? How many people even have temperature conversions on their calculator? A couple of them. Did you put in negative 40 for me, and what did you come up with? They came up with negative 40 again, right? So you can convert negative 40 to F or negative 40 from F to C, and guess what? Isn't that interesting? When you have numerically the same temperature, you'll have the same degree of hot and cold in those degree C and degree F temperature scale. So there you go. Where was E thinking? We got 3 E's. No, come on now. So when we get to chapter 3, we're going to talk about properties of refrigerants. And refrigerants make things cold, and our ice cream likes to be at maybe negative 10 degrees F, etc. And so they want a temperature that's sufficiently low, and they pick negative 40 because it's the same hot and cold that's in both degrees C and degrees F. And so negative 40 seems to be a benchmark by which a lot of thermodynamic properties for refrigerants starts and has like internal energy and enthalpy is starting at 0. Tuck that away. We'll get to it, chapter 3. 1 degree C temperature change equals 1 degree K temperature change. True or false? We're almost all in. 4 seconds. We're done. Are we 100% as a class on this one or not? I don't know what to say. Should I repeat it standing on my head to get your attention? Oh, no, no more spelling. Now we move to pressure. Pressure is force per unit area. True? If we do a weightless piston, I do this weightless piston right here. I have a downward directed force F acting. I have the pressure of the gas below it acting upward. Then that pressure acting over the area A, so pressure times A is a force acting up, and then I have the force acting down from statics, free body equilibrium on that weightless piston. P times A is equal to F. Or P is equal to F divided by A. That force per unit area. Make sense? That's what pressure is. We have absolute, atmospheric, and gauge pressure. So you can think about a gas. That's probably easiest to think about a gas, but we could talk about pressures in liquids as well. Don't really talk about pressures in solids because solids can be stretched as well as compressed. And you can't stretch a gas or stretch a liquid. You can push on it but not really pull on it. So we have absolute zero pressure. Zero pressure. What is that? Vacuum. Do we ever see that? And well, most of the distance between the sun and the earth is a state of vacuum. There's not much out there. There's a stray little gas particle floating around, but it's pretty good vacuum. If you want a pure vacuum, an absolute perfect vacuum, you got to get every little gas molecule out of there, and it's really hard. It's really, really hard. Just like getting all the way to 0 Kelvin, it's really hard to get there. You may get to 0.1 Kelvin, 0.01 Kelvin, but the physicists work really, really hard to drive it down to lower temperatures. 0.0001. I don't know what the lowest temperature is achieved in experiments and labs, but I think it's like 10 to the minus 8th Kelvin. Same thing here. Get all the gas molecules out. You'll have a perfectly hard, absolute zero vacuum. There's no pressure, zero. All right, then we come up here and we have atmospheric pressure. That's like the air pressure in this room. It's about 1 atm. How big is that in kilopascal? Well, 101.3 kilopascal. How about psi? About 14.7 pounds of force per square inch. So it's atmospheric pressure. We're in it in this room, but we don't really feel like it's that burdensome, right? It's atmospheric pressure. And then gauge pressure is everything above. So here's absolute pressure, here's atmospheric pressure, and there's gauge pressure. And then if you measured a vacuum pressure, it would be typically measured from the local atmospheric pressure down. All right. What's a barometer used for? Barometer is used to measure what pressure? Barometric pressure. What's another name for barometric pressure? Atmospheric pressure. The barometer is a tool used to measure atmospheric pressure. So let's do this. Let's build up this concept slowly. I know everybody's familiar with this, but here's a vat of a liquid known as Hg. Hg stands for mercury. We don't want to play with vats of mercury, but in our conceptual thought experiment, there's a big vat of liquid mercury. I take a test tube. Maybe the test tube looks like this. It's open on one end, and it's long. You know what? I need that test tube to be at least 30 inches long. Some of you don't think in inches. All right? I need it to be 76 centimeters long, at least 70, which is 760 millimeters. That's how long I need it. Everybody, I need you to take your 2 fingers, 2 hands, and I want you to show me 30 inches or 760 millimeters. Got it? Some people got like the bass fish I caught last weekend. No, hey, come on now, 30 inches? That's a big 30 inches. All right, so, all right, you got it? It's not like this. It's like that. Thank you very much. Now, I need it that long, so let's double it. That's how long this glass, what do I call it, test tube is. It's open on one end, and it's sitting out here, and I'm holding it in the hand, and it's surrounded by, I'm not trying to be tricky here, air. What fills the test tube? I'll keep asking that question. I got it out here in air. I'm going like this. What's inside the test tube? Air. Now I take it and I put the test tube, the closed end, I push it down, the open end's up, still in air. What's inside the test tube? Air. Then I take the test tube and I bring it under, well actually let me do it this way. I take it and I put the closed end up and the open end down, and I just bring it down and push it down. What's inside the test tube? Air. Now the mercury will maybe have gotten a little bit inside because the air is being compressed a little bit, but it's primarily all filled with air. Okay. Now I take the test tube and I tilt it underneath such that the bottom is lower than the top. What do you think happens to that air? Bubbles out. What's inside the test tube? Mercury. Is there any air in that test tube? No, it's all filled with mercury. Then I turn it like this, and I'm about ready to start lifting it. What's inside that test tube? Now I bring it out. And remember, I have to have a long test tube, so I bring it out just a little bit, and then I bring it out a little bit more, then I bring it out a little bit more, then I bring it out a little bit more, but I never let that end come out. It's always there. And what I notice is that this right in here, what do you think's right in here for the first case? It starts to come out, an inch or two outside of the mercury. What's inside? Mercury. Mercury. And then I lift it, and the mercury's still all in here. But then something special happens. The mercury doesn't go up any higher. And then even if I lift it out, remember I have to have a really long test tube. The mercury is just at this level. It's a glass test tube. I look. The mercury is a silvery, metallic type of fluid. I can see that's mercury. There's no mercury above that little line of mercury inside the test tube. So now I'm left with a very perplexing question. What's inside the test tube right there? Vacuum. And sometimes I'll get people to say air. I'm glad I didn't hear air. What did I hear? Air. What did I hear? Air. I don't hear the wrong answer. I'm sorry. Sometimes people, air. How'd the air get in there? It's not air. So it's a vacuum. But okay, vacuum, hard, perfect vacuums never come by. So what exactly, describe a little better than just saying a vacuum. What's in there? A few little mercury vapor molecules floating around. And at that temperature, mercury doesn't like to be in a vapor. But there will be some. So don't take it and breathe, that's why we don't have open pits of mercury and people working around them, because it's going to have some mercury molecules coming off. You'd breathe them, get in your lungs and other things. All right? You don't want that. It's not healthy. So right up in here is basically a vacuum, which means because it's so few vapor molecules of mercury there that it's very low pressure. So we take a little chunk of this and we pull it to the side. What we're going to do is we're going to grab this little section right here and we're going to pull it to the side. It's like a little cylinder of fluid like that. And we're going to do an FBD, free body diagram on this. And what's the pressure pushing down up here on the top of that? 0, because it's a good vacuum. I know it's not precisely 0, it's 0.0000 something, but it's close enough to 0 we'll say it's negligible. Then we'll have, for the free body diagram, big W. I forgot. What is big W? The weight, which is the mass of the mercury in that column times G. Then what do we have on the bottom pushing up? The pressure. I cut it right here. Is the pressure right here and the pressure right there the same? Yeah, it's the atmospheric pressure pushing down, the air beating down on the mercury outside. So this is PATM. That's the atmospheric pressure. So what happens is in equilibrium, I have the weight acting down is equal to the atmospheric pressure times that area of that fluid column. That's typically a little pi d squared over 4, some round area acting up. The weight is the mass times G. I already wrote that. What is the mass of the fluid in that column? Well, it would be the density of the mercury times the area times the height of that fluid. Height, H. Is that the mass? Rho times the volume, A times H? Yes or no? Yes. Good. And then we multiply by G. Mass times G gives us the weight. Then we have this is equal to the atmospheric pressure times the area. Can I cancel those areas? Are those the same areas? Yeah, it's the same area. And so we have an equation that says the atmospheric pressure is equal to the density of the mercury times the height of the mercury times G. And so sometimes you hear the weather, oh, it's 29.9 inches of mercury and rising. Oh, it's 29 point something inches of mercury and falling. And basically you have a measure of the local atmospheric pressure, and when you have a weather front push in and push out, that mercury in the barometer fluctuates just a little bit, and if you're very attentive you could see it go up or down. Let's take the same barometer, the same mercury. We're going to go and visit Denver, Colorado. Why Denver? Its elevation is a mile high. It's a mile high, right? We're going to go to Corpus or Houston, essentially at sea level, versus up there. Are we going to have the same height of the mercury in the barometer? No. Which one's going to have a lower column height of mercury in the barometer? Denver or Houston? Which one's going to have a smaller? Denver, because it's higher elevation, the lower atmospheric pressure. The pressure, the atmospheric pressure pushes it up in that barometer. Make sense? This is the man, Torricelli, Italian scientist, the years he lived. And we honor him to this day by saying 1 atmosphere of pressure is 760 torr. Basically, a torr is a millimeter of mercury column height. Millimeter of mercury height in a barometer. So 760 millimeters of mercury. Sometimes they'll say, oh, what's the pressure? Oh, it's 759 millimeters of mercury. Well, you say, millimeters of mercury, height of a fluid, that's a ridiculous unit for measurement of pressure. No, it's not. It makes sense with the barometer. Here's a picture of him. What do you think he has in his hand right there? There's a statue of him. What do you think he has in his hand right there? Well, Professor, I'm glad you asked. We have 30 seconds. In the monument of the Italian scientist Evangelista Torricelli, I think I butchered his name, what instrument is he holding in his hand? Thermometer, barometer, hygrometer, potentiometer, or manometer? Why do we have 6 people holding a thermometer? We're talking pressure. We're talking pressure. Mercury versus water-filled barometer. What's the density of mercury? What's the density of water at 4 degrees C, which is our standard density? We like to measure it. We say, hey, 4 degrees C, it's its densest. It's 1,000 kilograms per cubic meter. What's the density of mercury, room temperature? It's 13.6 times the density of water at 4 degrees C. So it's 13,600 kilograms per cubic meter. It's 13 points, the specific gravity is 13.6 times greater. I mean, that's the number for it, okay? So the density is higher. So I said for the barometer that was mercury filled, we needed to have a height of that one because we anticipate the height to be 760 millimeters height. True? Let's say somebody says, I don't want to work with mercury. No. We want to work with a water-filled barometer. How tall does the water-filled barometer need to be? How high? 13.6 times. Look at the equation, 760 millimeters. Okay, let's see how many meters that is. So 0.76, that's almost, it's 3/4 basically of a meter, multiplied by 13.6. Professor wants a number, there it is, 10.3 meters. Those that are SI, they can visualize how tall that is. For those that aren't, they have to say, well, I need to convert that to feet to make some sense of it, right? How many people can convert that to feet? Let's go ahead and do it. What do you get in feet? Did you get about 34 feet? All right, take a look at me. Size me up. How tall am I?
6 feet.
6 feet. We're going to round off to the nearest integer on the height. 6 foot. All right, 34 feet. You going to be able to fit a 34-foot water-filled barometer in this room? Put me against the wall, double me. Can you do that visually? That'll get you to 12 feet. 12 feet. Take that, double it. That'll get you to 24 feet. That's 4 of me. All right. We need to still get up to 34 feet. That's why we use mercury instead of water-filled barometers. Thank you very much for your attention. We continue next time.